Welcome everyone, my name is Zsolt Tóth from the University of Miskolc, and I'm here today to talk to you about comparison of two Wi-Fi-based indoor positioning techniques. First of all, let's talk what does indoor positioning means. Indoor positioning aims to locate to determine the position of objects or even people within buildings or a complex of buildings, multiple buildings. This indoor positioning systems have many challenges, and these challenges come from basically the signal attenuation, reflection, and multipass effects. The other question of indoor positioning systems: what does the position mean? In some cases, we want to determine absolute position. The absolute position is basically coordinates in a coordinate system, and the coordinate system is given. It can be fixed. It can be fixed a local coordinate system or like the GPS coordinate system. It can be a proximity-based position, like next to the window. It's next to other well-known object, or symbolic position within a building, in the first floor, and so on. The precision is another question of indoor position systems, and the precision and the required precision is application specific. For example, we are looking for a people. 2 or 3 meter precision is quite good because we can find someone in 2 or 3 meters. It's good enough. But if we are looking for objects, for example, boxes or something, 1 meter can be a huge range. So if you, for example, looking for your keys, the key won't answer your calls, and it's hard to find, for example. Let's see an example. This is the map of the University of Miskolc. Basically, it's in Hungarian, but it's not a problem. And we are looking for the lecture hall 26. The result of the system can be a GPS coordinate, for example. A local coordinate is defined in the university. A proximity-based position can be next to the label 101. Okay, where is the label 101? Or a symbolic position which says it's the Institute of Information Science. So this indoor positioning system could have a result with a different position for this question, or where are we question. Okay, so let's see what kind of indoor positioning systems or solutions there are on the market or have been published. First, let's see the technology. From the point of view of technology, there are different solutions. One of the first solutions is the active batch system, which is based on infrared. It was developed by the ET&T labs. It put infrared emitters in badges, and the people had to wear these badges. The active batch uses ultrasonic technology, and in this case the emitter will put into the ceiling. Both of them have advantages and disadvantages. There are recently there are research is on RFID technology, like the landmark or the spot-on systems, which is good because the RFID chips are quite cheap. For example, the landmark system in the landmark system there are many passive RFID chips put into the floor, and the reader is put into the located object. And there are Wi-Fi-based systems. We're focused on the Wi-Fi-based positioning because the Wi-Fi-based systems are even cheaper because we had already installed the Wi-Fi network in the institute, and that's all. There are numerous solutions in Wi-Fi-based systems, like the radar systems of the Microsoft Research Labs, Echo, which is a software suite, and I think it's a commercial software suite. Horus is another university project. The basic techniques is there are two basic techniques. First is lateralization based or triangulation, as the previous speaker said, talked about it, and there are other recently more popular technique which is based on skin analysis. It is also referred as fingerprinting methods. The lateralization methods are based on distance calculation, and this distance can be based on time of arrival or received signal strengths. The skin analysis are usually based on received signal strengths, and it has two phases, an online and an offline phase. In the offline phase, it collects data, and based on the collected data in the online phase, it uses statistical or classification-based or nearest neighborhood methods to calculate the position. I will detail it in our tests. So let's see the standard lateralization methods based on distance calculation, which comes from the received signal strengths in our case, and the calculation of the distance from the position based on the coordinates. So we have a equation, and based on this equation and multiple access points, we can formulate equation systems. It required installed access points and which position is known, and it's used for absolute positioning. And the other disadvantages of this system, this technique, is that it requires at least 3 access points to locate an object. Moreover, in indoor environment, the line of sight is not guaranteed. On the other hand, the well-known GPS system use these methods. Or tested methods based on that, we have recognized that there is an error in the calculation, and this error is the dashed line in the figure. We calculated this error, and we wanted that our position be within this purple polygon. We wanted no exact solution, but a close solution would be nice. So we formalized a problem as a minimization problem, and we wanted to minimize the error, the sum of error, basically. And to solve this optimization task, we used simulated annealing and a genetic algorithm search. The parameters of our search is the dimensions of our actual position. Okay, let's see. Fingerprinting method techniques are based on 2 phases, as I mentioned a few minutes ago. In the offline phase, the measurement application collects the data in known positions. It's passed to the system. This is the system part. The measurements will be cleaned, filtered, and stored in a database, which is called radio map or fingerprinting database. Next to the measurements, some heuristical methods is trained or tuned after. Recently, we are working on a neural network-based solution, and it requires both training and tuning. After the offline phase, there is an online phase when the users come with a localization application. The localization application samples the signal strengths in the space, and the sampling is put to the localization service, the localization service also filters the data and compare the received information with the database, the radio map. Then it gives back the similar measurements and based on the similar stored positions, it calculates a possible position for the device. That's some kind of approximation. There are two questions. First of all, what is the radio map? A radio map was basically a relation database which stored two information. First, the coordinate of the GNOME measurements, which is a three-dimensional, and it stored absolute position, and the measurements for the given coordination, which stored the access point and the average signal strength in the given point. And logically, we handled this like a set of access point and signal strength pairs in a given coordination. And the other question is the distance calculation. We used two distance calculation methods. The first was based on Euclidean distance, and the second was based on correlation. In the correlation distance calculation, we used threshold, and the measurement was similar to our local position in the sampling of the local position if the correlation coefficients exceed the threshold. Okay. To perform this measurement, we have created a client-server-based application. The server stored the business logic, and it was implemented as a web service, and it had the localization interface, of course. The communication was based on JSON messages, and the client was a smartphone and implemented as an Android application. It performed the sampling of the signal strengths, then called the localization service, basically. Or we have tested we have tested these techniques in the first floor of a three-story building, which is the Institute of Information Science, and it's 27-meter length and about 40 meters in the other direction. We had 4 access points during the measurements. 2 were already installed in the institute, and it provided a data network, and we put 2 additional Wi-Fi routers in specific positions. Okay, let's see our results. Our trilateral results use only 2-dimensional data because it was one-story building, and we held the phone in the same height during the measurement. Our results are given in meter. We can see that the standard method was quite good. It could achieve about 5-meter precision with 75 in the 75 percentile. And the heuristic methods show that the genetic algorithm had poor results. It may require some tuning or set better settings of the parameters of the genetic algorithm, but the simulated annealing had a quite good result for this. And the fingerprinting results is the following. Our experiment shows that the correlation requires high threshold, first of all, and our precision was in this case between 4 and 5 meters, but the Euclidean, with the Euclidean distance, we had the best results, and in this case, the error was within 3 meters, most of the errors, basically. And we find that the average is higher than the 75 percentile because there can be some outlying error, high error in some positions. And we found that this high error position was under a lamp. And this lamp had an automatic switch, and the switch, when it turned the light off or on, it made our measurements bad, basically. So let me to sum up our results. First of all, we implemented trilateration and fingerprinting-based methods as a web service, and we created an Android client to perform the measurements. Our precision were between 3 and 5 meters in one floor. And our future work is that we are going to implement a reference systems to compare our solutions with that. We are currently working on a model-based approach, which is based on which uses neural networks, and we want to implement client-side filtering in the mobile phone to improve our precision and pre-filter our measurements. And thank you for your attention.